Hello, student. Welcome back to this topic of magnetoelectric composites. So, in the last session, I have discussed so many uh, things or matters related to this magnetoelectric composites, and now I am going to talk on already the reported. Values of magnetoelectric coefficient for the different systems studied by the different researchers. So here you can see this represents the type of connectivity I used during the study of the research or during the study of these composite materials, and this color is used for the 03 type of connectivity, and this symbol is used for the 13 type of connectivity, and this is used for the 22 type of connectivity, and this is for quasi one dimensional type of materials. So it is very clear from this diagram that you can see here two type of connectivity. Very large number of researchers have used the two type of connectivity. That means they have fabricated the layers of the composite material, layers of the different materials, and they are kept one over the another to make the composite, so thereby getting the two type of connectivity. So here these are all bilayer composite materials. This side some bilayers, tri-layer composite materials are there. And what is the difference between these composites and these composites is that the range of magnetoelectric coefficient values obtained for these composite materials is less. So it is less than 6. So that is why they have grouped separately, whereas the ME coefficient obtained in this class of materials is having very high value. Note that this is volt per centimeter oversted. Then, so these are the very high values of the magnetoelectric coefficients obtained for different different systems. And here, this is the barium titanate and cobalt ferrite and barium titanate tri-layered composite material. It is having the maximum some 5 point something value for this ME coefficient, and some other composite materials like this. It is alloy of iron, cobalt, silicon, and bismuth, and metaglass, PZT. So many composite materials are prepared. So the value of ME coefficient is going down as you come down. And this side, you can see the highest value of the magnetoelectric coefficient is obtained for this bilayer of metaglass and PVDF. So it is polyvinyl. It is a piezoelectric material, and so same values is also obtained for this bilayer of metaglass and PM and PT, and some another metaglass with PZT, metaglass with PZT, PZ and PT, terphenol D with PMNG. So many composites are tried for the different researchers, and these two have came out as the bilayer composite materials which possess the maximum value of magnetoelectric coefficient. So one can immediately know that these are the two very important guys which can be used for the device fabrication. Here also I have given the list of some reported magnetoelectric composite materials. The reference is from 2003 to 2017. And you can see here two categories of the ME values are given here. On left hand side, these are the non-resonance values. That means when the applied frequency is not is below the resonance value or above the resonance value, then the measured values of the piezoelectric ME coefficient are given in here. So for this bilayer composite material, this non-resonance value of ME coefficient is 22.90, whereas for the same material, same composites, the resonance value of the ME coefficient is 7,000. Resonance value of ME coefficient means when the applied AC magnetic field is matching with the natural frequency of this material, resonance takes place between the two frequencies. At that time, what happens, because the piezoelectric material present in this combination of composite will be vibrating or oscillating with high frequency, maximum frequency. Because of that reason, very high voltage is developed across the material. So because of that reason, at resonance, very high values of ME coefficients are obtained. And for this another bilayer ME composite, 20,000 resonance value of ME coefficient is reported, and non-resonance value is not reported for this. And it is very clear that non-resonance values are very less. ME values of the ME coefficient values of the non-resonance values, non-resonance state or non-resonance conditions are less as compared to the resonance values of the ME coefficient, and they are very, very high values. So what is the idea is that as these composites are responding to a maximum value or maximum state for that resonance, applied resonance frequency, generally the devices are fabricated around that resonant frequency, so that the response of the ME composite material will be high. So at the resonance frequency, the devices are fabricated and the good results are obtained. So very huge resonance values of the ME coefficients are obtained for these two ME composites. And now we'll see what are the applications of these ME composites. And these ME composites are used in spintronics, where the spins are manipulated, sensors, memory devices, MEMS, energy harvesters, gyrators, and microwave devices. And some of the applications I am going here in detail. So this is the ME transformer. We know the transformers are used to transfer to either the step up or step down the applied voltages. The regular transformers we have seen a bulky device with iron core and copper winding like that. Generally, it is a bigger device, and the transformers are fabricated using these ME layers like this. It is a 5-layer device. The 5 layers are laminated one over the another. 2 layers of metal glass will be there, and 1 layer of PZT layer at the middle, and again 2 layers of metal glass are or sand or laminated one over the another. The size of this device is seen here. It is just 100 length. That means a 10 centimeter length is there, and 1.2 centimeter width and 3.6 centimeter thickness is there. Sorry, 0.036 centimeter of thickness is there. And the advantage of this ME transformer is that it is like a strip, a metallic strip, and it can be fitted to some bottom layer, or sometimes that means where the regular transformers are not suitable in some applications, these ME transformers can be used. So these are the smart magnetoelectric RAMs. RAM means it is a random access memory. Two types of memory we have seen. One is the permanent RAM, permanent memory. Another one is the volatile RAM memory. So random access memory is generally a volatile memory. It doesn't store the information permanently, but it reads the information present in the computer. So different RAMs we have studied already. Computers are having the RAM, now mobiles are having the RAM. So these RAMs, whenever a program is opened in a computer, that opens in the RAM. So suppose if bigger is the program you have opened, you should have a larger values of RAM, otherwise it doesn't run. So that is the background of the random access memory, or that is the use of the random access memory in different applications. So the different types of RAMs are there. SRAM means the static RAM, static random access memory. DRAM, dynamic random access memory. These are the two basic types of RAMs already available in the market. And the problem is that these RAMs are controlled by the current. That means by passing the suitable current through that memory chip, the reading action of the memory takes place, and hence these uses more power and they are of low speed. So that is a problem with these RAMs which are already available in the market. And the ROMs designed with these magnetoelectric materials are referred as the smart RAMs, and these are represented by MERAM, magnetoelectric RAMs, and these uses the very low power consumption is very low, and they are referred as the four-state RAM, because you can see here a square loop is obtained when you are changing the applied electric field. So four states are possible. So that is why it is called as the four-state RAM. And high storage capacity. The storage capacity is also very high as compared to the basic or regular RAMs. And 180-degree rotation. That means the information stored in the RAMs is rotated through the 180-degree. So this is necessary for reading out or storage of the information. And basically it consists of the 3 layers like this, and they are parallel to each other, and here they are anti-parallel to each other. So generally they are in the means actually it consists of one piezo. This is the piezoelectric layer, and these are the ferromagnetic layers, and they are polarized oppositely. By applying some electric field to this structure, you can restructure or change the orientation of the dipoles present in the material, thereby it permits us to store the data. So this is the another device called as the device which converts current into voltage. It is called as a gyrator. So this gyrator type of devices are used in the microwave applications. So here it is like this. Again, it is a three-layer structure or device. It works in LT mode because the magnetic layers are parallel, they are longitudinal, whereas the ferroelectric layer is polarized transversely. So that is why it works in the LT mode, and these are the equivalent circuits, and these devices are used to convert current into voltage in microwave applications. So this is the very interesting topic called as the magnetoelectric energy harvesting technique. Here you can see these are all the electrical devices. It is a transformer, a huge transformer. It is a huge power supply. It is a computer CPU box. It is a washing machine. It is a water lifting pump. It is a floor mill. It is a generator. It is a fan. All these devices are working on a huge current, except this computer. Others are working by making use of huge AC current, and they are producing a very large amount of electromagnetic field around them. For example, this transformer is working means it creates a large amount of electromagnetic field around it. This is a high power supply. It also creates very large magnetic field. Here, all these applications, very large amount of magnetoelectric field, electromagnetic field is created around these devices, and that energy carried by the that electromagnetic field is wasting. So is wasting if you are not using it. So the idea is that these cantilevers, these are a cantilever type of things fabricated with magnetoelectric materials, and here in these devices, ME harvesting devices, very high response ME composite materials are used, like earlier I shown in the diagram. Some bilayer composites are having very high values of ME coefficient, like 55 volt per centimeter roasted was there. So that kind of ME composite with a very high value of magnetoelectric coefficients are used in these devices. And these devices, what they will do, if you are keeping these devices, if this device near to this working devices, electrical devices, this devices absorbs the electromagnetic field or radiation emitted by all these devices. It receives the electromagnetic field distributed or given out by all these mechanical devices, because so many copper windings are there in all these systems. Motors are there, high currents are flowing. So yeah, so in everywhere the electromagnetic field is created. So that field it becomes the is the stimulus for these devices. So if you are keeping these devices near to these appliances, it starts working and it could produce some voltage. It will develop some voltage here. So that voltage can be used to charge the batteries, all those things. So this is the concept of magnetoelectric energy harvesting. So same idea is also used here, magnetic energy harvesting. So this is a simple case. Even the power carrying cables, it is a power carrying cable is there. So a large amount of current is flowing through this cable. So according to the Maxwell's law, according to the Maxwell's law of electromagnetics, so whenever, or it is a very basic idea that whenever a current is flowing through a conductor, a magnetic field is always created around it. So that can be detected with the help of Maxwell's thumb rule. So here you can see here stray magnetic field is created around this cable. Or this is a black color ring type of thing is a stray magnetic field created because of the flow of current through this cable. So this small magnetic field created around this power cable is utilized to start working of this magnetoelectric composite material. So as soon as the current flow starts flowing through this cable, what happens? The magnetic field created by this cable will enter this EME composite material. So once it enters the EME composite material, the piezoelectric effect starts taking place, and because of that reason, the electric voltage is developed across this material, and that developed electric field can be used uh, to 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 charge the low power consumables like these batteries. We can use that power generated here to recharge the batteries. So, or you can use this for any low power consuming appliances. So this is the concept of magnetoelectric energy harvesting. Here just you are using the waste electromagnetic field created around a power carrying cable, and that is utilized. That is what is called as harvesting. So here another harvester is designed, and it is published by this Jimbashi et al. So this is a device which is used to convert the stray magnetic fields nearby or around some electrical appliances, and they convert that into a voltage. So here it is very clear that measured potential as a function of distance between the device and the power carrying appliance. So if you are moving these devices away from an electrical appliance, the potential developed will be less. It is as expected. So this is about EME sensor. You have heard about Hall probe. So that is used to detect the magnetic field in between the two electrodes or anywhere where the magnetic field is present. But the problem with that Hall probe or Gauss meter is that it can't detect the magnetic field if it is in the nano Tesla range. If the magnetic field produced is in the nano Tesla range, you can't use the Hall probe for its detection. So for that very high sensitive ME sensor, ME magnetoelectric sensor is needed. So this device, which is developed by making use of magnetoelectric composites, can detect the magnetic field which is in the nano Tesla range. So that is the very, very important point, or very, very important application of this ME sensors. So ME sensors are the only alternative in the low magnetic field regions. ME antennas. We have heard about antennas. Antennas are used to radiate the power into the space. So different kinds of antennas are there. VHF antenna, very high frequency antenna, and UHF antennas, ultra high frequency antennas, and VLF antenna, very low frequency antennas are there. So different kinds of antennas we have studied. So the size of the antenna is the biggest problem in most of the cases or in most of the applications. Sometimes the size of the according to the frequency and amplitude of the power to be radiated, the size of the antenna will be decided, and sometimes the size of the antenna becomes very big. So that is the biggest headache. So in order to avoid that problem, the researchers have found the antennas which are constructed based on MU materials, and the speciality you can see here, this antenna is, for example, just 10 centimeter length. It is a 10 centimeter length. So the size of the antenna is very, very small. And what is the speciality of this ME antennas is that small in size. This is very, very important. These antennas are very small in size, and they consume the low power. Low power consumption is the another very important parameter, and high theoretical radiation efficiency. This is a very, very important point. The radiation efficiency of an antenna is very, very important. That decides whether the antenna can be used or not. So the antenna should have the high theoretical radiation efficiency. So this high theoretical radiation efficiency is achieved in case of these ME materials antennas, ME antennas. So this is another biggest application of ME materials. So this is about tunable RF ME inductors, magnetoelectric inductor. So inductor means it is generally it is a copper. In normal inductor, it is a copper coil. Depending upon the number of turns in the coil, the inductance value of that device is determined. But here, these materials behaves as an inductor. So then these are used in RF mode, means radio frequency range. These inductors are used in the radio frequency applications. And the very important point is that these are the tunable RF ME inductor. You can tune its inductance value by changing the dimensions or something. So that is a very advantage. And fast tunability. The tuning is also very fast, and these consume the low power. This is very, very important because the normal inductors consume a lot of power as they produces the eddy current whenever the current starts flowing through them. So that eddy current problem is not here. Eddy current problem is solved here. So these are the new inventions of the MU material. So this is all about MU materials and their applications. And I have tried to give a small introduction of this magnetoelectric composites and their applications. Nowadays, it is a huge field. It has emerged as a big branch of physics, and very lot of work has been done by the many researchers, and a very large number of devices are also have been fabricated by the researchers. So just I have tried to give a glimpse of this field, and thanks for watching.